we now have understood how you can have a vector space and you select a subspace and you have an orthogonal complement. So you have a vector space that can be written as U, the subspace you chose, plus its orthogonal complement. This will bring to us the idea of what we will call, in precise terms, orthogonal projectors. Or orthogonal projectors. Now, these projectors are very, very useful. Perhaps I should make this story very simple first and give you a little intuition. If you have, say, a three-dimensional vector space, any vector has three components, the x component, y component, z component. You could imagine a linear operator that acting on this vector gives you just the x component of the vector. Gives you a vector, a new vector, that just has an x component and is equal to the x component of the vector you had. That would be a projector into the x direction, into a one-dimensional subspace, and the y and z would be the orthogonal directions. You could also have a projector that gives you, acting on any vector, a vector that is along the y direction and whose magnitude is equal to the component of the original vector had in the y direction. And that would be a projector into the y direction. So projectors are the things that take a vector and forget a lot of things and just concentrate on some parts that you like. This is a projector down to a subspace. And basically what the projector does is takes the vector. By virtue of the theorem, we proved that U plus U perp are a direct sum decomposition of the vector space. Any vector can be written as a U vector plus a vector in U perp. Then you forget about the vector in U perp and you just keep the vector in U. And that's a well-defined operation. So when I mention this case of three dimensions, how would these projectors look? The projector is a linear operator, so it should be thought as a matrix. So if I think of a vector V as having components V1, V2, and V3, for example, a projector into the x direction would be a matrix 1, 0, 0, 0, 0, 0, 0, 0, 0. That would be a projector into the x direction because acting on any vector, for example, acting on V, it would give you Px. Acting on V, it would give you V1, 0, 0, which is what we said you should do. You should take the whole vector and just keep the x component. So this is a projector. If you have a 1 in the middle and the zeros everywhere, it's Py. If you had a 1 here, it's Pz. So projectors are not complicated things. We want to understand them in more detail, not necessarily all the time looking at the matrix representation, but we want to understand where they come from and what properties they have. Why? Because after all, in quantum mechanics, there's a postulate, a measurement postulate, in which a state is evolving and you do a measurement. And then the wave function collapses into an eigenstate of this operator you're measuring. And after that, it is in that eigenstate that you measured. That operation that brings you from the general state to an eigenstate would be a projection operator. So projection operators are the key operators in order to understand measurements. That's why we're going to pay some attention to them. So let me state this now in all generality. So this was for you to get oriented. because we begin always stating things in a very general way, and this may not be completely clear. So let's define the operator that we want to define. So this is going to be an operator P for projector, and we will put a U because it projects into U. So this will be the name, P U. This will be a projector that projects into U, and it's going to be a linear operator. So it's a projector to U, and it's, of course, a linear operator. And how does it do it? Consider for any V in V, this V can be written as U plus W, where U belongs to U and W belongs to capital W. And this decomposition, as we discussed before, is unique. So any vector, you can give me those two unambiguously, these two vectors. So this is what the operator PU does for a living. PU acting on V gives you just U. You can think of this PU, that's a definition. For that vector, so whenever you act on any vector, this is what you must do. You must decompose it as a vector in U plus the rest. You throw the rest, and you keep that. That is the projection operator. And it's a linear operator. You would have to show it. This is the definition. And it's simple to show. It's a good thing to do that. So that's, you could think of this also as well as saying PU. You could also view it as saying PU on U plus W is equal to, it's a linear operator, PU on U plus PU on W. And this is U plus 0. That is the definition of PU on V. But now that you know that this is a linear operator, this is how it's happening. PU is acting on this sum. On U, it gives you U. On W, it gives you 0. So let's think, what can we say about this operator, the projector operator, some properties of the projector operator. So this is called an orthogonal projector, because it uses the orthogonal decomposition. PU is an orthogonal. Here you should add the word orthogonal projector there. So why don't I do it? Might as well. Orthogonal. Now, projector. So facts about this orthogonal projector. Let's list a lot of facts. Facts. 1. What is the null space of the projector? It's the set of vectors that are killed by the projector. Well, if a vector doesn't have component in U, it gets killed. So any vector in U perp is killed. So the null part of this is U perp. All of the vectors in U perp get killed. So that's it. So since the null space is not empty, unless U is the whole vector space, this operator is not injective. Injective was when the null space was 0. And it's not invertible. So PU is not 1-to-1. Not injective. You take a vector, and it gets sent to something. You add a little bit in the orthogonal complement, it gets sent to the same thing. So PU is not injective, not invertible. Already we learned something. How about the other question about operators? We said that when you meet an operator, you first ask them what is your null space, what is your range. So let's do that. What is the range of PU? Well, the range of PU is all those vectors that you obtain after you're acting with the operator PU. And you certainly can obtain any vector in U, because if you apply the projector to any vector in U, you get that same vector. So the range of PU is U. So PU is not surjective. The range of P is not the full space. Two important properties. Let's go on. Let's restate that PU acting on U is the identity operator. So if a vector is in U, well, when you act with the projector, the only thing the projector does is kill the component in U perp. So if it acts on a vector that is in U, it gives you the same vector. So whenever it's acting on the vector space U, it's just the identity operator. Whenever it's acting on the vector space U perp, it will be 0. Now let's write a formula for the action of the projection. If E1 up to En is a basis for U, then Pu on V gives you what? The component of V, or the part of V in U, and that is E1 V E1 all the way up to En V En. Maybe this requires a little clarification. Certainly, you see that the result is in U, as it should be, because you're projecting down to the space U, because it's a sum of ENs. Now, you may remember from a previous time that, in general, the definition in an orthonormal basis, and this is what we'll have here, an orthonormal basis, you can write any vector is an orthonormal basis, ON basis. You can write any vector in this form, but for the full vector space V, you would have still the basis vectors corresponding to U perp. And that was the formula we had for writing a vector in terms of its basis vectors in an orthonormal basis, the inner product times the corresponding vector. So this sum for the full vector V would include those basis vectors in U perp. But they're killed by the action of the operator Pu. So therefore, this is what you get. This is the action of the operator on this space. Now, another property that is very famous, actually, arises from thinking the following way. If you have Pu acting on V, as we did before, you get U. If you have Pu times Pu acting on V, well, you use associativity, so you evaluate this first, and it would be Pu acting on U. But Pu acting on U is the identity on U, so this is just U. So what you discover is that pu on any vector is the same as pu acting on the vector. So pu is the same thing as pu. This is a very famous property. People say a projector satisfies the square of the projector is equal to the projector, because the projector, one projector does all the job. The first projector will take a vector and put it in the subspace. The second one is already in the subspace. It acts as the identity, so it has no purpose. So this equation is true. Now this equation, sometimes if you're a little careless, you would say that this equation already means that you've got a projector, but it's not quite true. You don't have an orthogonal projector if you have just this equation. You also have to state other things. So this is necessary, but not sufficient to have a projector. Nevertheless, it gives you a lot of information. Maybe I'll put a sixth property, which is kind of intuitive and nice. It's the norm of pu on v is less than or equal to the norm of v. That's another property of the projectors. Should be intuitively clear. If you have a vector and you apply a projector, you lose some perpendicular component. So the vector that you get is smaller in length. So once you apply the projector and calculate the length, you get less than what you had before. And you can think of this, think of the inner product of v with v. Well, we said that any v can be written as u plus w times u plus w. And this is the length of v squared. Now here, u and w are orthogonal, so you don't get the mixed term, but you get u and u, w with w, which is the Pythagorean theorem. Is that right? If you have an orthogonal decomposition, the length square is the length square of the first summand plus the length square of the second summand. So this vector is the length squared of PV. So the length squared of PV is here because P acting on V is the vector U. So this, the length of V squared is bigger than the right-hand side if you take this away. So this is bigger than PV squared because I throw away this, and therefore PV has smaller length than V. Very nice property as well, and fairly intuitive. Well, another thing we said about projectors that, or that about any operator, that the way to learn more about them is to think of the eigenvectors and eigenvalues of the projectors. And this is a very simple story. It's nice that it's very simple, and I want you to have it really on the tip of your fingers all the time. If somebody asks you about eigenvectors and eigenvalues of projectors, the answer is very well known and very simple and intuitively clear. And you can think of this in this way. You want eigenvectors are invariant subspaces of the projector. So let's think of a basis of U. Projector PU. Any vector in the basis of U is acted by the projector is left invariant. Just exactly invariant. Even the magnitude is not changed. So the basis vectors of U, where you're projecting, acted with the projector give themselves. So these are eigenvectors of eigenvalue 1. Any basis vector of U is an eigenvector with eigenvalue 1. any basis vector of U perp is killed by P. So it's an eigenvector with eigenvalue 0. End of story. Very simple result. So I will write it here. The orthonormal ON basis vectors for U are eigenvectors of PU with lambda equals 1, because they're left invariant. The orthonormal basis vectors for U perp are eigenvectors of PU with lambda equals 0. So it couldn't be simpler. And this could have been anticipated from this equation. You see, if an operator satisfies an equation, we've explained before that the eigenvalues satisfy the same equation. So lambda squared is equal to lambda is an equation that should be satisfied by eigenvalues of the projecture operator. Therefore, this equation is lambda times lambda minus 1 equals 0. And it says here that the eigenvalues of the projector are either 1 or 0. Each eigenvalue must choose. And we don't know how many 1s or how many 0s. That depends on how you construct the projector. There are projectors to different subspaces. You will understand that very soon. So, all right, so we have our understanding of eigenvectors and eigenvalues of the projectors. Now let's talk a little about the matrix representation. We started with that at the beginning of the discussion, and let's go back to this. So I'll consider the case where I have V, U plus U perp, and I will have a basis E1 up to En of U, and F1 up to Fm, no, up to Fk. This is a basis for U, and this is a basis for U perp. And it's all an orthonormal basis. Everything is orthonormal. This is an ON basis for the full vector space V. And you can ask the question, how, if we have chosen this as basis vectors, this is going to be the first basis vector, the second basis vector, the nth, the n plus 1, up to the n plus k basis vectors, I should be able to represent this matrix as a n plus k times n plus k square matrix. So the projector PU must be an m plus k times an n plus k matrix. N, k, k. And we think of this as the first basis vector, the second basis vector, the third basis vector. Now, what does the projector do on the first basis vector? It gives you this first basis vector. So the first basis vector can be viewed as a column vector in which there's a 1 in here and zeros everywhere else. So this will be obtained if you put a 1 here and the corner there. And therefore, on the first basis vector, you will get the right answer moreover, let's say this. If this first basis vector acted by the projector must give you the first basis vector, it must give you nothing else. So there should be zeros here as well. So that will guarantee that if you have 1, 0, 0, 0, 0, 0, 0, whatever this matrix does on this vector is giving you back this vector. For this second vector to work, you will need a 1 here, zeros, 0, 0, 0, 0, 0, zeros everywhere. And then the 1s continue all the way here. So you need a 1s here, a big 0 here, a big 0 here, and a big 0 here. That will do the job of letting this projector act on any of the ENs. P on any of the EIs should give you the EI. But P acting on any of the FJs should give you 0, because P is in the orthogonal subspace. So you should get 0 whatever you put, whenever you put any of the vectors here. So actually, this will require a 0 here and a 0 there. So this is the projector for U. We put all the basis vectors in U, in the space you're projecting onto, at the beginning, and therefore we get a lot of 1s in the first entries in the diagonal, in the first n entries, and in the last n entries you get just 0. That is the projector in its matrix representation. It's the generalization of what we did at the beginning of this explanation. So a couple of things that we can discuss. Remember when we had our discussion that matrix representations are great, but they're basis dependent. So what part of the matrix representation is basis independent? Well, one part of it that is basis independent is the trace. So what is the trace of PU? It shouldn't depend on the basis that you use. So the basis we have here is good enough. So here we must sum the elements in the diagonal. Zeros here and 1s in n. So this is n. But that happens to be the dimensionality of U. So this is a very beautiful result in which the trace of the projector gives you immediately the information of what dimension vector space you're projecting into. And so this is a very nice result. And this PU is then called, PU is a rank n projector. Rank n meaning that it projects down to a subspace of dimension n. Another property, maybe a little less spectacular about this projector, is that the determinant, which is another invariant of PU, is 0. You cannot get a determinant because you don't have more than this one. So, and this was expected to be the case because anyway the operator was not invertible and was not injective. It had a null space. So if it's not injective, it's not invertible, and not invertible means the determinant is equal to 0. So that's another property of projectors. So there we go. We've learned the basics about projectors. All the projectors we will be discussing in this course will be orthogonal projectors. And those are projectors that, as you now have learned, arise when you have a decomposition of a vector space. And that decomposition is one in which you find first a subspace, and then you say the whole vector space is that subspace, direct sum, the orthogonal complement, the orthogonal subspace. And when you have that, then you have a linear operator that projects down to the original U space, and that operator will have the properties we've discussed.